I'm Jamie Allen. I'm the Director of Consulting for TypeSafe worldwide. So that's why I'm over here. I'm meeting with partners such as Software Mill and Virtus Labs. They're consulting partners of ours who do really good work for their customers. So it's really great to meet with them in person. I'm also the author of Effective Akka, which is a book from O'Reilly. It's a very thin book, but that's for a reason. It was meant to be a book that was friendly for putting on a mobile device or something like that and give people a lot of advice in a short amount of time. So,
and as a matter of fact, if I may interrupt you, I was about to buy, several copies, but because I knew about your coming too late, it didn't arrive. So
yeah.
We've got a couple of copies, so I'm gonna draw, and put you in a happy mood, having one of those copies.
Oh, cool.
Yeah.
Yeah, and most of the stuff that I'm going to talk about here in the talk is from the book. So, you'll get a lot of the material from the book, just from having attended. So I've been doing actor-based development for almost 5 years now. And at first I started out with the Scala actors, which I don't know how many people have played with the original Scala actors. Anybody in the room? Yeah. They were a pretty true implementation of Erlang and some of OTP, the concepts of the Open Telephony Protocol. But they didn't really work well on the JVM. And the reason for that is that when you follow the rules of OTP, you're going to do something called selective receive. And that means that when a message comes into an actor, you're going to either handle it or you don't. And if you don't handle it, it's going to be put off to the side, right? Now, you get another message, and you handle that one successfully. Now you look at the messages you have off to the side, and you replay them. And the reason for that is because actors can change their receive block based upon having received a message. So the message that came in successfully handled, may have changed the receive block for that actor, and now the messages that were off to the side can be replayed to see if, they're valid now. Well, on a platform like the Beam VM in Erlang, this works well because you have very strict isolation of processes. However, the JVM is a monolithic process, and you don't have the isolation that you do in the Erlang VM. So in the JVM, using Scala actors with the selective receive concept, you in essence have a memory leak. If you don't ever handle these messages, they're sitting here off to the side. Every time you do successfully handle a message, you replay all of them, and they may never still get handled. What a waste, right? Now in Erlang, that's fine. But on the JVM, like I said, over time, this builds up a cost. And, Akka had already been implemented and had already thought about these things, and, we just decided that Akka should be, the reference implementation of actors in Scala going forward. Because it didn't make sense to have two different implementations. And there are other really good reasons for this as well. There are other things put into Akka that made it a better choice. So I started out with Scala actors, and then, 3 years ago or so, I started doing Akka. So fair amount of experience with working with actor-based development. This is not an introductory talk. How many people here have played with Akka so far? Awesome. If you haven't, some of this is going to sound really, really bizarre. But I'll just tell you this up front. Actors cannot be talked to by simple method calling. You have to send messages around in actors, and they get put into a queue and handled in the order in which they were received. And they get handled one at a time. So there's no concurrency inside of the actor. This is why it's a powerful concept for maintaining a non-locking, non-blocking kind of architecture. There are other ways to implement very similar features, such as communicating sequential processes. CSP, which is what you see in Clojure's core.async, and you see it with Go channels. They're powerful concepts as well, and they're sort of a dual to actors. What they do is they operate on green threads. They're going to use a thread by multiple different parts of the application, right? And they don't queue messages. You can have priority for how they handle, but they have to sync up. Two individual operations that are happening in your application sort of have to meet up at a point and then go forward. Now, these two different ways of doing things both have their use cases, right? With actors, the primary difference is that you are getting this thing called location transparency. The location of your actor could be anywhere. It could be in this JVM, it could be on another JVM on the same box, it could be on a completely different box, it could be in a completely different data center, but your code never reflects that. Your configuration drives the location of where the actors are in your topology, and then you merely have to say that I want to send a message to this actor. And everything about Akka, and really Erlang as well, will handle sending the message to the appropriate actor wherever it's located. So the other primary difference between CSP and actors is this concept of fault tolerance, which I'll explain a little bit more later. So does everybody kind of grasp what this is all about? Yeah, okay. So I have a couple of patterns that I developed, and they're very similar. Has anybody ever heard of the Saga pattern inside of actor development? No? Okay. Yeah, one person is nodding. They're very similar to it, but they're a little bit more constrained. And these are a couple of patterns for how we can handle when we want to be able to receive messages, but not have our actor think only about that message while it's doing stuff. You can have an actor receive multiple messages, and if it handles one at a time and then responds before handling the next one, that sort of builds up a certain amount of latency inside of your system. But you don't have to do that. What we can do is aggregate a context for a particular request. We could say that I've got a message coming in, and now I'm going to spawn something that is going to handle that particular request and do all of the work associated with it, and then respond to whomever asked for it. And that way, the outside actor who's receiving the messages, you can call it your API if you will, it can go on and handle more messages and spawn more things up to a certain point. You obviously don't want to do anything completely unbounded. So how do we do that? What are our options? I'm going to show you a use case here, and this is the use case I use in the book as well. What we're doing this, does anybody work for a bank or ever do any kind of financial services? Yeah, a few people, all right. So just as a very simple use case, imagine that you have an actor who is responsible for getting all of the account data for a particular customer. So the actor is going to receive a get customer account balances. But getting account balances usually isn't in just one place. You might have checking accounts, savings accounts, money market accounts, brokerage accounts, retirement accounts, who knows what, right? And that means that if you're going to aggregate all this information, you probably don't want to handle that request in a sort of synchronous fashion. You just want to, hey, go off and do this work for me and send it back to whomever asked for it, right? Actors should not wait to finish by handling a single request before handling the next one. And actors should have a dependency injection going on here, a constructor-based dependency injection. In this case, I'm not using any framework because that starts too many flame wars. But I am showing that my actor that's going to do this work is going to receive proxies in its constructor that tell it where to ask for savings account information, checking account information, and money markets. And either it should get all responses from each of the services within a certain amount of time, or it should say, well, I can't, I've got a timeout here, and communicate that somehow. So here's a really basic view of what it is I'm trying to achieve. I've got 4 messages in a queue here for my request receiver. And I'm going to spawn a different handler to do the work for each one of these actors. Does that make sense? Just going asynchronous here. And it allows that request receiver to handle more requests. And this isn't such a penalty that you're paying here, because actors, very lightweight. One of the reasons that there are 2 different kinds of actors, if anybody is really into the deeper theory of this, but you could have actors that are based on a thread, right? And those are heavyweight actors because they have a tremendous amount of resources associated with their instance, right? Just having a thread on the JVM is on the order of 5 kilobytes in size because it's got to have a stack associated with it and other resources. That's a pretty big penalty, right? What Akka is doing is creating lightweight actors, and they're sharing a pool of threads that they all can use. So, you know, we're not paying a tremendous cost by allocating a new actor for every one of our messages. In size, we're talking on the order of 300 to 400 bytes, plus whatever we put into it as well. But it's not that bad. It's not like we're creating something with a huge data set inside of it, particularly in this example. So, in doing something like this, when we're wrapping a context around a message, we're in essence sort of creating a transaction, right? We're saying that I'm going to have an actor responsible for doing this work, and I have all the knowledge I need to handle everything about this interaction with this context. It's all around me, right? I don't need any outside information. So say this was an example of instead of getting information, but setting information somewhere, putting account information into multiple different places. I have the ability, with a context like this, to say how to handle rollback. If something went correct here, but failed over there, I can put the behavior into my handlers to say what to do. And this is, in essence, very similar to a transaction. Is it as robust as using something along the lines of Spring transactions? Depends on what you write. But then again, the cost of using Spring transactions is you're using Spring. So, it's your call. So, all of the code I'm going to show you from this point forward is on my GitHub account. I'm Jamie-Allen, which can be a little confusing because I'm Jamie_Allen on Twitter. Whenever I went to GitHub and created my account, they wouldn't let me do an underscore here, so I went with dash. But you'll see that Effective Akka is the repo that this is all in. And you can clone the repo and see all of the code and all of the tests. It's updated with the latest versions of Akka and Scala, and using Scala test as well. So, you know, if you want to see any of this code and just play with it yourself, feel free. I don't make any, you know, restrictions or anything. It's all open source, right? So, one question people sometimes ask me is, well, futures and promises, right? And that's true. They can. And futures are a really, really nice functional concept for going asynchronous because we can do really cool things such as sequence futures. And by that I mean we could have a list of future int, future int, future int. And whenever I call sequence on it, I'm now turning it into a future of a list of int. I'm now sort of pulling out the fact that it's a bunch of futures inside of a list and making it a single future of a list of integers. That's really nice features, and you can do very powerful functional programming things with it. In my opinion, they have some cost associated with them. If you want to, you can use futures and you can capture the context, and promises are nice because what I can say is I either have one response out of many things I want to do, or none because it timed out. But each future that you use to do this is going to result in this sort of ask support thing inside of Akka, which you don't use, but Akka uses, to, you know, represent that future as an actor. For example, I can send a message in Akka, and instead of sending it with this fire and forget semantics, where I send it and then I'm totally not paying attention to what's going on, right? I can keep going asynchronously. Or I can use this ask semantics, which is me waiting for a response. But every time I do that with a future, I have to have a timeout for that future as well. So if I do this 3 times for every one of my requests for account balance information, that means I've got 3 other timeouts that are going to take place, 1 for each future I'm creating. So I think that that's a little more heavyweight. I can't really say based on benchmarks that it has a particular penalty associated with it, but cognitively, I think it does. So I tend to go in this other direction for other stylistic reasons as well, but you'll see what I'm talking about shortly. So here's an example of using futures. In the receive block of my actor, whenever I'm handling a message, I have cases for what messages I'm handling. And in this case, I'm only handling get customer account balances for a particular customer ID, right? And then I say, well, all right, I'm going to create a future of get me the savings account information. I'm going to create another future of get me the checking account information. And then I can create another future of get me the money market account information. And this is all going to happen asynchronously. It's going to fall through, and it's going to build up these futures and only successfully handle them whenever they all have successfully, returned a value. And that's enforced inside of my for comprehension here, right? I'm using a for to say that when I have a value for my futures of savings, I'm going to, because futures are untyped in the Akka world, map to an option of a list of long and big decimal. Now, you may say, why are you using an option here? The reason is that whenever I am receiving data back from one of these services, I have to make a differentiation between when it didn't work yet and when it returns no data, right? So if I have no response yet, I've got it, my option is a none. And whenever I do get data back and there's no savings information, it's an empty list. Does that make sense? Yeah. So, the long being the ID of the account and the big decimal being representation of the, money in the account somehow. Now I can map over these, and the sequential part of this is that for us to get our checking, we must first get our savings, right? Checking may come back before savings, but the for comprehension will enforce that it will not, get the value out of the checking future until the savings future is successfully returned. This is our binding of a monadic operation for those people who are really excited about functional programming. But it's not a detail you have to worry about too much whenever you're just using a for comprehension. So if we get our savings, and if we get our checkings, and if we get our money market data, we can yield an account balances, right? And we could either pipe it back to a sender, whoever sent us the original message asking for this information, or we could just map over the balances, which is a future of all of these things, and when it is fully completed with all the values from all of the people that we've asked for, it will send the value back. I like using this semantics more than pipe 2. Anybody who knows what pipe 2 is, just because this is a lot easier for some people to understand, because it's more like traditional Scala. People who understand actors, they typically tend to prefer pipe 2, and that's fine. I don't think it matters much.
Excuse me?
Yeah?
There is, this sender will be a good reference that we want to replicate?
No! But I haven't gotten there yet.
Okay.
This is one of the biggest problems that people will encounter whenever they're Akka developers. And since a lot of people in this room have played with Akka, you've probably seen this before. But yes, the question was, is the sender that I'm going to respond to who I think it is at the time that this comes back? Time is our biggest quandary in the asynchronous world. We have trouble dealing with time. And as an example of this, Roland Kuhn is the head of the Akka team, right? And he was looking into a way that he could do typed actors in Scala, and say at compile time whether or not an actor would be able to handle a specific message. And that's sort of a difficult thing because of the way that macro paradise is going, but don't worry too much about the details. I can talk about it later. But the one concept that we cannot prove or disprove at compile time is timing, right? If you have multiple receive blocks defined inside of an actor and you switch between them like a state machine, then I can't at compile time say that this actor is going to handle this message at that time. I do know that it will handle that message possibly, but I don't know that it will handle it then. So sneaky little things like this about asynchronous programming, it's not Scala, it's not Akka, it's Erlang, it's anything that's asynchronous. You're going to run into these weird timing issues. And in this case, sender. if I'm doing all this work asynchronously, and I'm saying, all right, go off thread and do this, go off thread and do that, go off thread and do this, well, by the time all of this is aggregated, this actor in which this block lives could be handling another message from another actor. And sender will then be that actor, not the one that who may have originally asked for this information. Don't worry, I'll talk about this more shortly. Yes?
Is this method sending back a lot of messages or just one?
Just one.
Just one.
Yeah.
Sender.
Yeah. The account balances. In this case, I'm using the underscore notation to say map over whatever's inside of my viewed balances, which is the yielded value of an account balance with the savings, checking, and money market option of a list, long big decimal. Yes?
Why you are not using in the last computation for each instead of map? Because for each is only for side effects. Map is for changing one value for other value.
Right.
And sender bank does not return value.
Here's the thing. I want to yield the final future of an account balances. If I do the for each, then I'm doing a side effecting.
Okay.
You know, that would do the asking and go get the information, but it wouldn't yield something.
Okay.
Yeah. Yes?
First of all, there is no error handling in this code. Is this supposed to be like that?
No, it's just size of slide.
Okay, and secondly, if you would use pipe 2 here, if you would just say viewed balances pipe 2 sender, it would be correct. Am I right?
No, sender would still be wrong, because sender, the implementation of it is a method inside of Akka. I don't know if you've looked at the actual Akka code.
Pipe 2 uses passing by value, not passing by reference, so sender would be...
Would it be the value returned at that time?
Yeah.
All right, plausibly. Then that might be an issue with this particular implementation.
Quite vague, but
yeah. All right. So, yeah, you know, capturing a sender, just like we were talking about, this is trickier than it sounds. You need the sender value from the actor that you want it to respond to, not whom the actor was currently working with. And I find this to be one of the biggest areas of bugs. So, you know, if I'm using pipe 2 and what you're saying is true, then I'm less likely to have this problem than if you're doing it the way I'm showing here. So, yeah, I've already talked about this sort of ad nauseum. Instead, we can use an anonymous actor, right? And in this case, you can call this sort of an actor lambda. It's an anonymous implementation of an actor because I'm saying create for me a new actor instance to handle and sort of close over the context that I need. So I'm saying here that, and I tend to use logging receive, by the way. This is a really nice feature inside of Akka, so that if you turn it on in configuration, it'll start showing you what messages were handled by an actor. But if I'm going to handle responses, right, I can say, all right, well, I've got this timeout thing that I haven't explained yet, but I'm going to stop it. It's a scheduled piece of work to compete against the completion of my work. And then I send the response of the successful receiving of all the information I want back to whomever I want. And I have a single method to do that because I could be sending back a timeout or the right answer. Now, this sort of defines how I'm going to handle what this anonymous actor will do. It will either receive back whatever answers I wanted, or it will time out. Right? Either way, it will send the response back to the whoever asked for it. And note, you always have to stop this anonymous actor. You have to stop yourself, otherwise this actor is going to live in memory and you're going to have a memory leak. I then send off the work I want to do. And then I define that I'm going to do some sort of, you know, I didn't update this slide, but this should be not a lambda, but should instead be calling the schedule 1, saying send to myself a work timeout. And I'm saying that within 250 milliseconds, I expect I should have gotten back my responses from the other services. But I'm not, I want to have one timeout mechanism competing against that, much like a promise would be, right? Queue of the actor's mailbox. Either the responses from all the things I wanted to get come back first, or the work timeout gets in there before all the responses do. And if the work timeout gets there first, I send back the work timeout message. So instead of having multiple futures with each having their own competing timeout, I have as many interactions as I want, and they have to come back to me before the competing single scheduled task. Does that make sense? Okay. But I call this the extra pattern, like an extra in a movie. They're there, they don't have a name, they're just a person that's walking down the street as, you know, two primary actors are talking about something. It's not bad, but anybody who knows about my distaste for lambdas will know that it has similar problems as lambdas do. For example, you won't know the name of this actor. You can sort of do it by giving this a name inside the definition here. It would be like down here. But even then, you would have to find a way to make sure they all have a unique name. Right? Yeah. So nobody ends up doing that, and they all end up seeing like $A or $B. This is name mangling. The compiler and the runtime really are coming up with a way to represent this anonymous instance of an actor. But also now, inside of my receive block, I put all this code. It's really cluttered up my receive block. Now, I could externalize it out into a method, but I'm much more inclined to instead define this as a type. You know, I can do a lot more as far as seeing stuff inside of my logs and handling things in a specific way by making it a type. So here is the anonymous actor example in full. What I showed you before was sort of a basic stub for how this would work. And inside of my receive, I say if I get a account customer, I know this is really small, by the way, but it's like I said on GitHub. In this case, I'm saying I have a new anonymous actor, and I'm defining a bar of checking balances, savings balances, money market account balances, right? And that's an option of a list of a long and big decimal. I should have been using long earlier in the presentation to represent the account ID because they typically are longs. And they're all none. I have no values at this point, right? And I say that inside my anonymous actor, if I get a checking account balance, put it into my checking balances, and then check to see if I've got all three. If I get a savings account balance, put it in my savings balances, check to see if I got all three. If I got the money market account balances, put it in the money market one, and then check to see if I got all three. And I have the account retrieval timeout here as well. If I get the timeout message, what do I do? So, the collect balances is now checking to see, do I have some value for C, some value for S, and some value for the money markets, right? If I have something for all three of those, then I know I can send the message back to whoever asked for account balances and cancel the competing timeout, right? If I don't have all three, if I only have the checking account, then the savings and the money market will be none. And I don't have to worry about doing anything right now. I can just say, all right, well, forget it. I'll wait until either the timeout comes in or all three. Binoculars, I'm sorry. I got to find a better way to represent this. So there's still the send, response, and shutdown. It's the exact same thing. And then I fire off the three messages to go get checking, get savings, get money market. And then I define the schedule once. And in this case, I didn't use the lambda. I used a method call where you can't close over state. So instead of doing it with that anonymous actor, we can instead pull that behavior out and put it into its own type. And I call that a cameo pattern because it's a lot like a cameo in a movie. You know, actors, we have some really great puns we can make. But these are name types. It's like seeing a movie and seeing, you know, a famous actor show up in it, like Michelle Pfeiffer, out of nowhere. She's there briefly and then she leaves. She does a quick cameo. And that's what this case would be. We externalize behavior into its own specific type, and anyone maintaining the code now has an easier time trying to figure out what you're doing, if you ask me at least. Most importantly, you can't close over state. So you may not have noticed because I kind of went past it fast, but the first thing I did here inside of my receive block for handling get a customer account balance was to stabilize the sender and put it into a val locally inside of this context. Now I don't have to worry that the sender is going to be a different sender than whom I first received this message from. And that's a really big deal. Because this is all going to happen asynchronously, right? So to create a Cameo actor, this is that simple dummy example, not the real world example, but now handle response and work timeout all within its own class actor with this receive block. The send response and shutdown is exactly the same. The context, dispatcher, and scheduling the work of going off and sending a timeout to me in 250 milliseconds, that's all the same. And then the delegating actor is going to create an instance of the worker, right? And it's going to call whoever is going to actually go get the information for them, but pass the worker as the sender. Like I said, always remember to stop the actor if you're doing anything like this where you're creating a context at a particular point in time. If you don't do that, then memory leak. And write tests. One of the things that a lot of people using actors don't do is write tests very well. And it's one of the things I end up helping people with a lot. There is a really magnificent testing facility inside of Akka. And it will allow you to test the behavior inside of an actor without doing any of the message sends. If you put stuff into methods, you can get access to the actor's underlying implementation, which is something you would never be able to do in prod. Right? In production, you would never be able to access the underlying actor class. You only have access to this thing called an actor ref. This is a really big deal, actually. The whole concept of an actor ref, just like a PID in Erlang, gives you this ability to not worry about the instance of an actor. With Scala actors, we didn't have this. And if an actor died and somebody else had a reference to that actor, I had to make sure they got a new reference to the new actor that was replacing it. That sucked. It didn't work very well. It meant a lot of useless communication. Akka and Erlang, they handle this for you through their actor ref and PID abstractions over the actor itself. Now, in your tests, if you use Akka's test kit, you have access to something called a test actor ref, from which you can get the underlying actor, and you can call methods on it, make sure in a unit test fashion that your behavior is what you expect. You want this. You don't want to put everything in your receive block and end up not being able to test it without sending a message, because that sucks. You want to minimize the amount of testing you have to do just by sending messages. But when you do have to send messages, it's really hard to test that you're handling multiple messages at the same time, but not interfering with one another, such as not getting the right sender to send back the value to. And there's a really cool facility inside of TestKit called a probe. Probe allows me to define a different sender, if you will, for every message I'm going to send into my actor to test this. And so, I'm using Scala test in this case, and I'm creating two proxies here. One is the checking account proxy to get checking account information for myself, and the other is a money markets account proxy. And there's stubs that I have inside of my repo if you want to see how they're implemented. And I say that an account balance retriever should return a list of account balances in. I create two distinct probes who are going to operate as the individual senders of my messages, right? I create instances of my proxies. And then I say, give me an instance of the account balance retriever. I say, within 300 milliseconds, send a message from the first probe, right? And expect that I'm going to get account balances back within 300 milliseconds, because I know my timeout is 250. And hash real timers, which is how the scheduling is done inside of Akka, is not a very precise mechanism. So don't expect that the scheduled task to compete against this is going to be exactly 250 milliseconds. It's usually a very lightweight scheduled thing. If you need something more robust, go with quartz or something like that. And I then do an assertion on my results. I'm doing a type assertion here. I'm doing an assertion on the values inside of what I got back. So two different assertions are happening here. And then I have another within 300 milliseconds where I'm sending from the second probe, right? The second probe is going, this is all going to fall through and happen asynchronously and put multiple messages into our actor's queue. And then when that happens, I'm testing now that my actors are going to handle multiple messages at the same time and get responses back to the right one. Should we take a pizza break?
Yeah, in 5 minutes.
I'm sorry?
In 5 minutes.
Okay, 5 minutes.
Yeah.
So what this is allowing me to do is test multiple actor interactions at the same time, right? And that's powerful. We need to prove this. It's not doing really heavy load, but as you build load tests, you'll want to do this sort of thing with multiple probes. So, write tests. Here's a sort of a zoom in of the withins that I had there before. Within 300 milliseconds, the first probe sends to the account balance retriever, give me the account balances for an ID of 1L, you know, customer 1L, 1 long. And I get a result based on expect message type, right? Forced equal account balances with these values. I got some checking, I got more savings, I got no money markets based on the stubs that I passed in. But then that means that the stubs have to have this data built into them to return it for your actors. And the same thing goes for the second probe. We also want to check the failure condition, right? And we can do that by having one of the stubs do nothing. Instead of responding whenever it receives a message to go off and return to you information, have it do absolutely nothing. There's an example inside my repo, but just, you know, it's an actor that, you know, has a case underscore, do nothing. And now I know that because one of these is definitely not going to respond with an actual, you know, information about somebody's accounts, we will get our timeout. So we send the message for get a customer account balances 1L, and then we expect to get back the timeout. And we still know that we don't want this to happen too quickly. So I'm saying that I expect after 250 milliseconds, but before maybe 500 milliseconds, these are tough to tune sometimes. Expect that you're going to get a timeout. If you got a timeout after 100 milliseconds, that would be a failure of some sort. Right? Your scheduler somehow sends something back way too fast.
Yeah, that's correct. Can we time out for pizzas?
Yeah.
Okay. So let's have 15 minutes break for pizzas.
Okay, let's get started again. So actually it turned out we were in a really good place to break because I just shown you all this code and stuff like that. And now I was going to start off with the section about best practices. So, you know, we all want to be successful using a tool, and there are lots of ways with asynchronous programming, with Akka, with any tool you use, where you can stub your foot and hurt yourself. So I talk about some of the things I've learned over several years of actor-based development that have hurt me and how I've gotten around it. So one thing that we have sort of obliquely mentioned, very slightly, is this idea that you can close over stuff. When we were creating our anonymous actor inside of the actor body, we were closing over the sender. The sender was from outside of its context, right? Because if we used the sender inside of the actor, the anonymous actor's context, it would be the sender of the anonymous actor who doesn't have one. You know, nobody sent it the first message. The senders it has would be who sent it the responses of account information. So we're closing over sender and using sender inside of there. That's all nasty stuff having to do with lambdas and closures, right? Well, inside of Akka itself, when you create an instance of an actor, you may have seen me doing this, where's a larger representation? An example of where I did a context actor of, right? The JVM is creating a new instance of a class. And when the JVM does that, it collects metadata about the class from which it was created, right? That's just object orientation inside of the JVM. Well, there's a problem there. Some of the metadata that's collected is actually this. The concept, the open recursion concept, this inside of Java, right? Inside of the JVM, this reference to myself. Everybody knows this, right? So when I do this, the actor I'm creating now has inside of its metadata a reference to this actor. Which, if somebody were to get nutty and do reflection, they could then have a reference to your actor that is not guarded by the actor ref. So, to be honest with you, I've never ever seen anybody do that. But the Akka team thinks it's worthwhile enough to have a pattern to help you avoid this possibility. And the way we do that is to create a companion object for every one of our Akka actors we define. And the companion object is usually the sort of place where we put our static information, like messages, right? Things that aren't going to, that's not entirely true, but messages that don't have state, for example. Static things that aren't going to, just like companion classes and case classes sort of thing, right? Companion objects in case classes. So what we're doing here is by having an object, right? We have a props method with all the things we need to create an instance of our account balance response handler. And we create it inside of this object, which is okay because the this that is going to be referenced is this object. And there should be no concurrency or weirdness inside of the object, right? If you're doing concurrent stuff inside of an object, you've got bigger problems than Akka. Okay? So this is just a pattern for getting around something that theoretically will be fixed in SIP 21. This is the Scala improvement process. And SIP 21 is going to introduce these concepts of pickles and spores. What a spore is the idea that you can declare what you're allowing people to close over before you do the closing over. So you say, all right, well, I'm going to close over sender over here. Here's my definition saying I'm going to do it, but also capture that value, right? Stabilize it so they can't change on me whenever I go to use it. And, I'm not sure when SIP 21 will go in, but it's not going to be for 2.11.0, which is right now just about to reach release candidate 1. So, if you feel as though this is something you must protect yourself from, here's your answer. If you want to make sure that there's no way anybody could ever get a reference to a this of an actor, which is a bad thing because, actors should only talk by messages, not method calling. If you could do that, then you could potentially have concurrency inside of an actor because one thread calling through a method via this, and the thread that's handling the messages in the mailbox, right? So if you have to do that, do this. Keep your actors simple. Don't have actors that do a whole bunch of different work. But this is, in essence, the single responsibility principle, right? Anybody here ever read Uncle Bob Martin, his book, what was it? I forget what it was called, actually.
Clean code.
I'm sorry, clean code? Okay, thank you. He talks about the single responsibility principle. And actors, because they're so lightweight, we want to create bunches of them. Yes, it means that there's a lot of interactions that are going to happen. But we'll understand the context of what went wrong and fault tolerance a lot better if we have very granular responsibilities inside of our actors, right? If we start putting all kinds of stuff into an actor where it's doing all these different things, debugging also becomes really hard because you have to know what the actor was thinking about at the point in time when something failed. Whereas if you know that a very simple actor failed, you know what it was doing, right? It was only doing the 1 or 2 things it was responsible for, instead of the 20. So be explicit in your supervision. How many people here know about supervisor hierarchies? Okay, a fair number, but for those who don't, I'm going to explain it. When you create actors, you don't create them as just this thing that's going to sit off on its own, hopefully, because that'd be a real waste of resources. What you do is you create a hierarchy of actors. You have a root node, and underneath that you create maybe 3 actors. And underneath each one of those, you're building a tree, right? And any actor that has no children is a leaf node of your tree. So what we want to do is have very explicit supervision. What do I mean by this? Here's an example of, let's say that this is a cable TV company or something like that, right? I've got my root node all the way up here, and it's, it's just sort of the root of my tree. I've got 2 customers, because this is a very simple graph, or not graph, tree I'm building to show for an example. And then underneath my customer, I've got account 1 and account 2, maybe my business account and another one's a home account, or maybe I have 2 homes because I'm really wealthy. I don't, by the way. But then I have devices. And the devices could be a set-top box in my bedroom with a DVR, another set-top box in my living room that doesn't have a DVR, another one is maybe my tablet or something, and they all have different rules about what TV you can watch on them, right? So underneath device 1, I've got these applications, underneath device 3, I've got these applications, but what I've done here is I've made my customer the supervisor for both accounts and devices. And this is bad. Now, it won't really bite you until failure starts to happen, but what's going to happen is I can only handle failure from accounts the same way I do for devices. And I may want different behavior depending on whether it's an account that failed or a device, even if it's the exact same exception that was thrown. And let's just say an illegal state exception happens here. If it happened in accounts, then maybe I need to restart all of my accounts and say, go refresh yourselves from the database and restart these accounts because they're bogus, right? But devices, I say, well, if one of them blows up, they're isolated, so, I want to only restart the one device that failed. I can't do that because I don't have a different supervisor for each type. Does that make sense? What I want is whenever I have this sort of thing going on, an accounts supervisor for accounts and a device supervisor for devices. It's a very simple example, and I don't need to make that split here until I have something else other than applications under devices, right? Because devices, by definition, are only handling applications at this time. But by doing this, now I can have completely different semantics about how I handle failure from accounts versus devices. Use failure zones. When people first start using Akka and they fire up an actor system which allows them to start creating actors in that supervisor hierarchy, one of the first things that they'll do is just use the default threading implementation inside of that actor system. And that'll work for them for a while because it is by definition a thread pool of say 8 to 64 threads, starting at 8 and then going up to as many as 64, assuming your box can handle that many threads. It has some other features about it as far as configuration settings, and they're all the defaults, right? And what people will do is they'll just use that default dispatcher until it starts to fall over. And by fall over, I mean you start seeing timeouts in your system all over the place. Because now you're scheduling more work across all of the actors and maybe some futures you're defining, right? That, that one dispatcher can't handle. So you're not properly isolating, your actors from one another. Say, for example, you've got actors that are going to go off and hit a database. How many people currently use a non-blocking database driver? 1, 2, 1. React to Mongo or something?
Yes.
Yeah, okay. So there are asynchronous drivers for MySQL and Postgres. I'm not sure they're JDBC compliant as far as the API goes, but yeah, they're asynchronous, and that's great. But it's very difficult right now to be completely non-blocking throughout your architecture if you've got legacy databases there. So what do? If we were to use the same dispatcher for all of our actors here, and have some of them going off and doing blocking interactions with the database, then the blocking ones are going to start to starve the other actors of resources. They can't access the thread because they're being held up by these blocking things down here, right? That's bad. So what we want to do is create a separate dispatcher just for blocking interactions with the database and let everything else that is asynchronous use a different thread pool. That's a very simple example, but these are the sorts of things you want to think about when you're dividing your application up by dispatcher. You want to put specific kinds of blocking operations on their own thread pool, maybe only with one thread. This is all about tuning. It's also relevant to think about the physical layer underneath what you're defining inside of your JVM. You can say in your JVM, if you've got enough heap space, that you want 10,000 threads. You can do it. It won't stop you. But what is the point of doing that, right? That doesn't make any sense whatsoever. So don't, you know. When you're really sitting down and trying to tune your Akka application, and you want to create these failure zones to bulkhead your actors from each other, and by bulkhead I mean like a ship. You know, you have your bulkhead so that if one of the parts of the ship gets pierced, like the Titanic did, you know, water won't rush into all compartments. It'll only go in through there, and you can hopefully shut the bulkheads of the ship and therefore not worry about water sinking you, right? That's the idea. So here's an example using a very similar thing from before. This is with my explicit supervision. I've got customers, I've got account supervisor, device supervisor, I've got my accounts over here, I've got my devices over here, and my applications at the bottom. But they're all using one thread pool. And it's going to start to starve one another as, you know, these maybe have blocking operations inside of them as they collect information from the devices, or the applications on the devices that they represent. Well, what we can do is separate them out and say, these are going to share a thread pool. This, all device, non-device specific information, but all device interactions other than that will be on another dispatcher. Accounts will be on their own dispatcher, and everything else in the system on its own. Just as an example, it's, you know, more to think about than just this. Don't willy-nilly create dispatches all over the place, but think about your system and how you want your system to be separated from other parts of the system. Because Erlang, again, great isolation between processes on the Bean VM. JVM, not so much. When things go wrong on the JVM, it affects the rest of the JVM, right? There's nothing you can do about it, whether it's memory, whether it's, you know, access to resources like threads. You know, this is the trade-off we're paying in order to have Erlang-like semantics on a much faster platform, but also monolithic JVM. JVM is a wonderful piece of engineering, but we have to know how to use it. Right? This is more of a guideline. It's not a rule of thumb. Don't say that I'm saying always do this, but you want your system to flow. You want to push messages. Yes?
May I have a question about the previous slide? Are there any drawbacks of using failure zones you may want to share with us? Something.
When you share or what?
I mean, are there any drawbacks of using failure zones? And, well, along the lines, why aren't failure zones default when you use supervisors?
Why aren't failure zones the default when you use supervision? Because we wouldn't be able to give you your ability to say where you want to start bulkheading. Yeah,
but you seem to insist on using failure zones because they are so important.
Yeah.
So if they are so important, why they are not defaults for, you know, some kind of constructs in Akka, like when you create supervisors, or, you know, I don't know. I'm not very fluent in Akka.
Part of this is that Akka is not really a framework, right?
Oh,
it's more of a toolkit that's going to give you the tools to build your system, sort of like Lego blocks, right?
Okay.
It's not, but it's more of the Lego blocks that don't make a Millennium Falcon or something like that, right?
Yeah, does this mean that Akka, because this resembles my feelings about Akka, does this mean that what we are saying, that Akka might be too low level for some use cases?
It's not for every use case, that's for sure.
Okay.
Yeah, I mean, what generalized toolkit is, right?
So what Akka misses compared to frameworks?
You're not going to say,
you're
not going to be able to download Akka and then say, all right, Akka, create, and it's going to build an application for you with scaffolding or anything like that. It doesn't do that.
Okay.
It's just merely a bunch of library classes that give you the functionality to build what you want.
Okay.
But then, you do have to understand what they are.
Okay.
Yeah, there is that trade-off.
Okay, thank you.
Also using only the default dispatcher is, in my opinion, a good idea if you don't use blocking API.
Yeah, even then, not so much. It depends on what you're doing. Because yeah, if you've heard of the throughput setting. Throughput is the number of messages my actor should handle before releasing the thread. And it's an up to kind of thing, right? By default, it's 5. And I'm saying that handle up to 5 messages in my mailbox before I give the thread to another actor. And what I'm defining here is fairness, right? I'm saying that I'm going to allow my actor system to be reasonably, or my dispatcher to be reasonably fair. Ultimate fairness would be handle 1 message and then give it back. But that wouldn't give you much in the way of batching, right? Batching is always a really good way to improve your performance. And so what we allow you to do is set your throughput to any number you want, but generally speaking, once you get above 100, we don't really see performance improvements. That could be it could be an effective Amdahl's law. How many people here know Amdahl's law? Yeah, this is when it comes to parallel programming. And okay, example. Right now, the dispatcher, by definition, by default, is using fork join pool. How many people know fork join pool? Yeah, this is in Java 7. It was a really great advancement in thread pooling because A, you didn't have to come up with a million configuration parameters, right? But it also spreads work across cores. That's hot. We love that. Flip side of this, in Scala, we have parallel collections. How many people use parallel collections? Don't. I'm kidding. It's up to you to define whether or not parallel collections are actually valuable because we are dealing with Amdahl's law here. We're spreading work across all the cores on whatever box we're running, and while this is a recursive breakdown of whatever task we have, say we have a list of 1 million numbers, and we want to add 1 to every single one of these. We know that that's commutative. It doesn't matter what order it's done. We know that it's associative. The grouping doesn't really matter at all either. So we can put this spread across all of our cores, and that's fantastic. But then what's the cost of the join at the end? Is the cost of joining all of the values that you have calculated at the end greater than if you just kept it on a single core and just run through the numbers really quickly? I don't know. It depends on what you're doing. So we have to measure that. We have to do little micro benchmarks to figure out whether or not it's worth parallelizing. Or do we want to run on a single core to do this? And pump data through real quickly and take advantage of low-level programming to get as much through as fast as possible, like people like Martin Thompson do. Really incredible high-performance programmers on the JVM. So, back to my point. Because we don't do joins in Akka, because we're talking about using fork join pool, but not actually joining at the end like you would with a parallel collection, we don't have this cost of Amdahl. Not here, anyway. So there may be an Amdahl's cost on the throughput of saying I want to handle 100 messages before I let go. If I said 1,000, I'm seeing a diminishing return. But play with it. It's up to you to figure out how your application responds to your changes of configuration. And giving you this capability is really powerful because now you can do the tuning based upon the number of cores you're running on, how fast your CPU-bound tasks take, how fast they can be done. So it's really important. Any more questions about this? I know I went on a bunch of tangents there, but there's just so many things we have to think about, regardless of what we're using. Java is about to implement their own parallel collections in Java 8, and we're just laughing. I mean, They put up 5 things that they wanted to kill Scala with, pretty much. I mean, that's not entirely true. I don't think they're looking to kill Scala, but they're certainly looking to compete, right? And, you know, Lambdas, my personal opinion, you know, they have their pluses and minuses. I love functional programming. Lambdas itself, neither here nor there. But, you know, the other things like completable future, that's awesome. Now they have futures as good as what we have in SIP 14. You know, optional. Now they're going to have options in there that are going to be just like Scala's to a degree. At least, yeah.
No.
Semantically, you can define now that this is an optional value versus something that should never be null. Right? That's good. But, you know, the way they did it, of course, by not giving it the same interface as, you know, other, yeah. You can't use the same semantics of how you wrote, how you dealt with the future, or how you dealt with the collection, and how you dealt with optional. You can't do that with Java. You know, defender methods and traits, we're actually extremely excited about the traits because this will allow us to write bytecode that is so much better than the junk we have to do now to make traits work on, you know, JDK 6. It's great to have them, but yeah, we got to jump through some hoops, right? We got to create an implementation class and an interface for this stuff. And you know, sometimes initialization order, anybody who's worked with traits has probably come across initialization order issues, right? It's...
One question, FAQ.
I'm sorry?
And then Paul Phillips, one question, FAQ.
Oh, yeah.
That's why my trait chose null pointer exception. So
it's a hard problem. Some of this is actually fixed in Scala 2.11 anyway. So, I mean, it's you know, railing sort of against a dead horse. It's like, yeah, but that's... And you were there when that was done, Paul. Yeah. Anyway. All right, I'll just address this right now. Paul is a great guy, and TypeSafe, you know, he's friends with all of us. We've been working together for years. But for one thing, TypeSafe doesn't make the libraries. We don't make the language libraries. That's the EPFL, right? And we hire compiler developers because if something goes wrong in your application and you need help, and you know, it's because the compiler's blowing up on you right now, you can't wait for an open source developer to be done with their day job to help you out, right? You need help now. So that's why TypeSafe builds the compiler and gives, you know, guarantees of correctness to companies who are going to use it. But the language libraries are still the EPFL. Paul wants to work on language libraries. We just don't do that. You know, we have enough work to do. People want the compiler to be faster. Yes, that would be awesome, right? There's a whole bunch of things that people want, and you know, a new collections library is really low on the list of things that people are asking for right now. So yes, would a new collections library with Paul's ideas be great? Who knows? It might be. Go Paul, you know? That'd be awesome if he's right. But it's pie in the sky right now. Nobody knows if it's going to work. And so here's hoping that Paul comes up with something awesome. It would be similar to Java and Guava. Right? Anybody ever use Google collections and stuff like that? Yeah, instead of using the Java ones, there's a bunch of collections libraries out there. Like Goldman Sachs is a really good collections library. It's open source on GitHub. Who knew? Right? You know? It's harder in Scala because they're so integrated into the language with Lambda support and stuff. So, you know, it'll be interesting to see what he comes up with. I hope he succeeds and makes something awesome. But, you know, right now he's being quiet again. You know, I hope he's hammering away at his computer, because that's what he does. He's a hacker. He loves to hack. So, anyway, so there's Paul Phillips. I really do like Paul. He's a great guy. So yeah, anyway, back to my push don't push. We want flow in our system, right? We want it to sort of move in a certain direction. And when we do asking, remember that question mark with the futures that we saw earlier? That's us saying, all right, well the flow is going to go here, but then come back, right? And we sort of have that whenever we're responding to messages, but it's much more of a loose flow whenever we're not making that contract for everything we do with ask. It doesn't matter how that request comes back to me whenever I'm doing much more of that push model. Now there are times, and somebody had a really good blog post about this, I forget who they were, but they were using Akka actors and they had a use case where pull was actually more performant than push. And that's great. You know, there's an edge case where something is better to go that way. But generally speaking, think first without guarantees. Make your system doing fire and forget, and not making rules about what I absolutely cannot possibly lose, right? And then you'll be surprised at how few things you actually do, right? Beware the thundering herd. This can be a really tricky problem with any kind of message-based system, where you send one message into the system and that makes everything change. And messages start flying all over your system, and you know, sometimes the same messages are coming to actors from multiple different places, just because the system got so large that the interactions became difficult to manage. And I've seen this happen. It's tricky. Large systems, messages, just event storms, as it were, right? Bad. You don't want this if you can avoid it. And this typically happens because you passed in a generic message. You said, account changed, or something, instead of saying, you know, checking account change for this customer with this ID. I mean, it's a really bad example. You would probably never do the first thing, but it's usually along that order. You said something that was really general, and everybody's got to respond to that, instead of allowing your system to route to the particular person who cares, and letting that particular actor do the work that needs to be done. And it may still need to go to multiple places, but at least you've limited the impact of your message send. You can still tune your dispatchers and your mailboxes with back-off policies and queue sizes. Bounded mailboxes are your friend, right? It is, by default, unbounded mailboxes in Akka. And I'm not really a fan of that. Generally speaking, you want bounded mailboxes, because then you have the ability to handle a specific amount of messages that will come through your system, right? And if you are getting overloaded, you aren't causing your system to bleed memory, bleed heap space, right? With bounded mailboxes, you're saying, I'm going to only handle 150 of these messages for this actor. And anything that doesn't fit in from that point, what happens? Anybody seen this? Gets dropped, it's in dead letters. It's great. Now, you're not going to sit, one thing I've seen some people trying to do is watch dead letters. That doesn't work in a distributed environment. What are you going to do if you sent the message to another actor, you know, in a whole other box, whole other node? You can't watch dead letters over there. You can only see what's happening on your own system, right? So instead, in those particular kinds of cases, you are going to have to say, look, either I got an acknowledgement that the work I expected happened, or I didn't and I need to retry. If I need to retry, that does mean that I have to think about, on the other side, what if I did handle it, but the response to ACK never went back? There are complexities involved in these systems. They're not for free. And if the problems were easy, then, you know, we would all just, you know, build it into a framework or something like that and just let it go. In this case, you have to think, just like you do when you're making the choice between UDP and TCP, or whatever the UDP kind is that also provides guarantees of delivery. I forget what that is. But we have to make choices about how and where we care about what happened and when. Akka also has circuit breakers. If you don't want to put it inside of your mailboxes, but you want to say, you know what, I want to handle like 10 of these messages, and then I'm going to sort of open the circuit breaker so that it's not going to handle anything for a little bit, right? It's a nice tool to have. And in this case, you will get an exception, right? This time you will know when you send a message to an actor with an open circuit breaker that it failed, even across into another node. So, handy. And I just sort of talked about this, creating granular messages that are usually the reason you get event storms. Unique IDs for messages are really, really handy. Because how do most people debug an asynchronous application, regardless of what tool you're using? Logs. Really, logs. If you're going to figure out what went wrong in production, you're looking at your logs. And there's a lot of them. But if you don't have unique IDs on your messages, you don't have a way to differentiate the flow of a particular message as it flowed through your system. Because then you can just grep. You take your log, grep it, and say, I only want all the log messages that had that particular ID, and boom, you can pretty much see what happened really quickly. So you don't have to use things like UUIDs. They're expensive, they're big, you know, but as long as you use some sort of hash that you are fairly certain won't collide within, you know, a couple hours or something, because you know when the failure occurred, right? You know you got a call at 3 o'clock in the morning on Saturday, right? So you know that, you know, if you go look at your server logs and you normalize the time for whatever time zone your servers are in, and you know where to find that, you know, so long as there's no collisions within a couple minutes, you'll be good, you know. So GUIDs are fine, probably even too strong. You know, if you have a hash that you know is reasonably good about collisions, you know, if you know the collision could happen the next day, who cares? That's fine. Akka ensures ordering on a per actor basis. So if I send a message from actor A to actor B, and then I send another message from actor A to actor B, I'm going to get them in that order, right? We guarantee that, even remote. But we can't make guarantees that actor A sending something to actor B and actor C sending something to actor B are going to be in some sort of order. You know, it's whatever comes in first. Create specialized exceptions. What's different about writing code with supervisor hierarchies instead of, you know, how did we handle failure before we built supervisor hierarchies? We have it all over the place. It's everywhere. Even with functional semantics, we end up putting failure handling logic all over our code. And what's different about supervisor hierarchies is they allow us to define a domain of failure. We're very good about thinking our domain of our application whenever it comes to all of the different types of entities that we have inside of our app, right? What we don't have is a failure domain. Nobody's ever really done this much before. But we can create that. Use very specialized error messages that only represent the kind of failure that happened inside this actor. Don't reuse it in another actor for, you know, a slightly similar kind of thing. Don't. Because then you'll know exactly what went wrong inside of your application when it blows up. And you see this cascading constant, you know, illegal state exception or something like that. Don't use that, you know. My account device, my device supervisor blew up because it didn't have the right number of applications below it, or devices below it. You know, things like that. Because when you know exactly what the failure is, as opposed to having to look and say, all right, this is used here, 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 and I know the line number over here, but that makes, what did that mean for that actor, right? Be explicit, and you won't have these problems. And an interesting thing here, this also gives you the capability to wrap information. Some state that is inside of your actor cannot be replicated sometimes. It's just a fact of life. Sometimes you have a class in Java, and there's state inside of it that you cannot possibly replicate. Maybe it was somehow time-based, right? Where you couldn't get it from the database again. It can't be recalculated. And if you have something like that that can absolutely not be somehow reproduced, you can put it inside of the exception and then use Akka's, you know, before I go off and restart and after I restart to collect that information and then put it back. So you can save it somehow. That's useful. You know, I don't do it a lot, but it's a hack, but it works. Never ever reference this. I was talking about this a little bit earlier. The open recursion concept of this inside of Java, Scala, other languages, right? Actors die, and therefore the instance of the actor, the instance of the class that was, you know, handling something and got an exception inside of it is not the same one, possibly, after it gets restarted. So inside of Akka supervision, you have a couple of choices. You could say, if the failure occurs, don't worry about it, just keep going. In which case, this is still the same. Or you could do restart. You could say, well, you know, I'm going to need to restart this actor and completely, you know, just start from scratch. And in that case, this will be different because, you know, it's an instance of a class. It's a new instance of a class. And like I said earlier with the old Scala actors, we didn't have this abstraction over this. It was painful. So never ever expose or publish this. You always want to think in terms of self with actors. Self is an actor ref to me, right? The actor that I am right now. So always use this instead, and use self instead of this. Don't use this. And you know, there's interesting things about self as well. If we were to write a class that's going to receive a message, and I'm not even talking actors here, but we receive a message, and then we're going to do looping for a long period of time. And then when we're done, we'll communicate with whomever sent us the message. We aren't communicating with our system at the same time, right? That can be a little painful, because until that loop is done, it's off doing its thing. And you're not going to want to interrupt that thread. Thread interruption on the JVM is a nerve-wracking experience. Anybody do it? Anybody ever do? Did it feel good? No. And what did you do whenever you caught the interrupted exception? Nothing? Yeah. Nobody knows what to do with it. It's true. I've watched some of the most brilliant JVM minds out there, like Kirk Pepperdine and Heinz Kaputz and Martin Thompson. They're all saying the same. Well, what do you do? Nothing. Oh, okay. There was a really long, prolonged debate about this. It was hilarious. And I felt so good knowing it wasn't just me. Well, instead of looping with some sort of while or for or something like that, what if we send messages to ourselves? Right? Yes, there is a cost in that we're, you know, creating, or we can reuse the instance of the message possibly, but we're putting it into a queue, and you know, the queue is going to use a thread, and the thread is going to now re-execute on the actor. Yes, that's not free, and context switching will abound. But the system, the actor system, and your other parts of your application can still interact with the actor. It's not just sitting there spinning off on its own, you know, out into space. That's great. Really, really useful semantics. So, you know, think about your problems in that terms. And if it matches, use it. If it doesn't, then hey, you know, loop. Here's an example of where you would register this. Anybody here use JMX? Really? Well, okay. I'll talk about this a little bit later. But with JMX, you have the ability to register instances of classes to be instrumented through mbeans in JConsole or Visual VM, right? And Akka will give you information about how well Akka is running and how well your application is running inside of Akka. It will not give you any information about state, right? It can't, unless we get all reflective, and that wouldn't be very fast or good. Instead, what some people do is use JMX. Because now I can register an mbean type, an interface, you know, trait, and say that I, you know, have these getters to get information out, like what is my current counter number or something like that, right? And then I can see at runtime what my state is. Now, in order to do this, I have to register a this of my actor instance, because, you know, JMX mbean server has no clue what an actor ref is. So you would have to register this. Now you're introducing concurrency in your actor. You're saying that I've got my thread operating on what's in the mailbox, and I've got the mbean server hitting my actor to get information through those interfaces, you know, for the counter's current number. You know, generally speaking, that's okay. You know, it's one thing to be all, you know, oh, you never do that, never ever do that. This is okay, it's not that bad. And you know what? It gives you visibility you wouldn't have otherwise. That's really useful. But, you know, if you were to put operations inside your mbean, and that, yeah, and that means that you have a method that you're calling to do something, that would be bad. Don't do that, right? And now you definitely have real concurrency inside your actor, and you don't want that, believe me. So, because I mean, that's one of the 3 reasons we use actors, to avoid concurrency. Yeah.
Java memory model, because if you have two threads accessing the same variable at the same time, and this variable is not volatile, you have absolutely no guarantee that the thing that sees that thread is the same that sees the another thread accessing the same variable, even it's when it's just reading, not writing.
I can even give you a use case of when that happens. I have an actor. It has a mailbox of 10 items. I'm using the default dispatcher, or maybe just the default throughput, right? So I only handle 5 messages, right? And I've got state inside of my actor. Now, those 5 elements, you know, five iterations take place based on, 5 messages are handled for that actor, and then it loses its thread, and then it gets another thread. It could be the same thread, but maybe it's another one. And now it's got to operate on this actor, and it has to have published the value inside of the actor here in order for it to see the correct, let's say it's a counter, right? That's what you're talking about, right? Yeah. Akka guarantees happens before. So happens before is a really important concept in the Java memory model, that we want to guarantee that values on a thread are updated before someone else will see it. And we only have certain ways to guarantee that will happen. One would be locks, right? If we use locks, we guarantee that threads will see new updated values. But we want to avoid locks. That's what we're trying to do in writing reactive applications, right? So we can use volatile. Volatile is a memory barrier. And using a memory barrier, you're saying that at the point in time when this value is going to be put, I'm doing a write barrier that guarantees this thread over here will see it instantaneously. But it comes at a certain cost, right? It means that I've now got to say that I'm going to push information cross-core, cross-socket possibly, on a box, and make sure that everybody sees this. Yes?
But if you are reading that variable, you have to put memory barrier, because CPU cores can have caches that need to be pushed to memory before you can read that variable.
By caches, you're talking about L1, L2, L0. L0 is only instruction cache, but I know what you mean. Trust me, Akka guarantees it.
Okay.
We're using SunMISC unsafe with lower level memory primitives than volatile to guarantee it.
Okay.
Yeah. And trying to be performant. So, you know, this is something that Victor Klang and Roland Kuhn spent a tremendous amount of time thinking about. And so far, I haven't heard of a case where we've gotten it wrong. So that's good. But publishing memory values across threads is tricky. It's not easy. And as Java developers, how many people understand volatile really, really well? I don't, and but one thing I learned recently was that I was putting volatile on multiple values that I was updating instead of put it on one and make that the last one, because then you get the happens before. It's like, God, I've been wasting all this performance on memory barriers I didn't need. Any change that happened up until the volatile will be published, as well as the volatile variable itself. So. Very, very important stuff to understand for multi-threaded programming on the JVM, regardless of what language you're using. The JRuby, Charles Nutter was making this mistake. He was like, God, yeah, all right, now I'm faster. It's little things. Immutable interactions. When we're on Erlang, we have the guarantee when we send a message that we're going to get copy on write. And that's fantastic, but it's slow. Even if you didn't need to copy on write, you're still paying the copy on write penalty in Erlang. Here, if you're going to have some mutable state inside of your actor, you do need to pay attention to the fact that you're about to send it out over a message, and another actor may be changing state that is internal to you. So don't make a copy of it, send that. Okay? And then also understand, how the JVM works from the perspective of references versus values, right? If you copy a reference to a collection to another reference, you're still pointing at the same collection. If somebody changes that, then you're going to get that change when you may not. You want to publish a snapshot, not send out the reference to your collection, right? Make a copy explicitly of it. Send that. But these are the problems we've been dealing with Java for years, right? Because there's no guarantees. Even with final, there's no guarantees of anything. Anyway. Yeah, externalized logic. So one thing I haven't really been showing here a lot inside of my examples is I've been putting a whole bunch of stuff inside of my receive blocks, and that's really bad form. Your receive block should just be a delegator. It should just have inside of it, when I get a message, go off and do this. And the reason is, now you're making very testable parts of your actor, you know, in methods. And they can be inside of the actor, and that's fine, but generally speaking, I actually would prefer to put them in library classes outside of actors, because then my behavior is not bound to the fact that they were once actor implemented. Yeah, that's a long-term view, but now if I ever need that behavior somewhere else, it's not an actor, I don't have to rip it out. I make functions and methods elsewhere, and now they're very testable without any actor semantics. No message passing, nothing. They're just, you know, they're just methods. Great. Because it had nothing to do with an actor that I wanted to check that if I went over 50,000 frequent flyer miles, I became gold status or something. I don't need to know that. I don't need to know that I'm an actor to test that, right? And the other really good thing about putting them in other, like, library classes and stuff like that is that you don't have to worry about closing over. There are times that closing over is awesome, right? When we're going to use things like currying, we want closing over. But for most things, most usages, it's just a good idea to minimize closing over, the possibility of it. Make sure things are always passed in as operands to a method or function. Semantically useful logging. You're going to see a lot of output with that, especially the more things you turn on, right? And you know, logging has a cost because nobody's got a really good logger out there. Log4j is coming out with the second version soon. It's going to be fully asynchronous, and that's awesome. You know, that's good. But we don't have that now, and we're not going to build a new logging framework either. So when you get output, you typically see all this stuff coming out, and it's all just a line and a line and a line. And sometimes it's really big, several lines. Somebody was complaining about this with the worksheet. Is that you? Mm-hmm. Yeah. The worksheet, you know, you see semantic output, or output that's not semantically useful because you can't read through all these things that were inside of a set. Rats. Well, you know what? When you're printing out your logs, format them. Don't just write stuff to the log, but give it formatting. Yeah, it means more lines are going to be printed, but you know what? You'll be glad whenever you're dealing with a failure, trying to figure out why some bad data came through, and you can see it really quickly, instead of line. Anybody else do this? I mean, I'm constantly looking like this. It's like watching tennis. So, yeah, both Akka and Erlang support hooking in multiple listeners to the event log stream. By this I mean that I can listen for specific events inside of Akka's sort of internal bus, right? Think about why you might want to do that. Think about why you're doing it before you do it. You can. Doesn't mean you should for this particular use case. Right? Don't tap in and listen to dead letters. You may have a reason you really want to. Maybe you have a special way you want to handle all drop messages. But no, you're going to be handling every drop message, and there's a performance cost associated with that. So think about it before you do it. Just don't go off and do it saying, yeah, I'm doing it. How many people here have seen the TypeSafe console? Yeah, we've done a really crappy job of making it available to people. You know, it's free to use for everybody, but you know, you gotta go and then you gotta register and say that you know, me from this company, and you know, it's like we've put more barriers in place of just letting people get stuff done. We're trying to get better about this. It's soon going to be rolled into Activator, and then you know, when you're using Activator, you just say, all right, go to the console view and look at your application running. That'll be great. What the Akka view of console does, and mind you, don't run in production. Originally we were using something very akin to the Dapper implementation that Google put a paper out about. Has anybody ever heard of Dapper? It's a way of sampling and stuff like that. But we quickly realized that we're just not a very good monitoring company. You know, there are companies out there that do this a lot better than us. And if you really want to get good monitoring, you should go to them. New Relic, App Dynamics, they're the people who do this stuff really well. So, you know, what we ended up doing here was load time weaving. It will slow your application down. Can you run it in production? Yes. Should you? It's up to you. We just don't recommend it. And somebody else is coming out with something called Datadog. It's a consulting firm in the UK called Cake Solutions. Anybody ever hear of Jan Mahacek? He's Hansom999 on Twitter. He puts out really awesome material and stuff, and he writes a lot of activator templates. Totally worth checking out. It'll be free, so Datadog, it'll be out soon. Anyway, the really important things you want to watch here are you want to see if your mailboxes are increasingly getting larger for your actors, right? That's a really big deal. It means you're not handling stuff fast enough, and you may need to parallelize your operations into multiple routees. You know, this is typically in the case of worker actors. Worker actors do not typically have internal state. They may have a counter or something like that. I don't know why you do it, but you know, they may have. They typically don't. They receive their state in every message, and they do work based upon the state that they receive, right? So you typically do routers and routees with worker actors. And then, you know, the other kind of actors you might have are the kind that are data actors. They're almost like your domain. So if you have worker actors and you want to see, are they handling stuff fast enough, or do I need to find a way to eliminate the growth of work that's not being handled fast enough by maybe spinning up another node in the cluster, you know, watch here inside of your console. The max mailbox time, the time between, this is sort of like Little's Law. How many people know Little's Law? Little's Law is that I am measuring the time when something enters a queue between when it's actually processed, right? And what you're seeing here is sort of a visualization of Little's Law. How much is that latency between when it actually gets handled from when it was put in?